Welcome back to our discussion of Chapter 31. This is the second video in the second part. So we're picking up with Section 8, which is on half-life and the rate of decay. So radioactive processes are very random in nature. In lab, we'll have a device to look at radioactive decay, and it makes a noise every time it detects something. So you'll hear click, 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 click. It's a very random sort of thing, but over time, the averages work out. So we will be looking at rates of decay over time intervals. So the half-life is the time required for half of your radioactive sample to decay into another type of atom. Half-life is always measured in units of time. It can be milliseconds or millions of years or even billions of years. There's a wide range of half-lives that are available. So for example, if you had 100 grams of radioactive isotope and in 30 minutes, instead of 100 grams, you only had 50 grams of your radioactive isotope and 50 of something else, then the half-life would be that 30-minute time interval, that 30 minutes that it took from going from the full 100 grams to only 50 grams. Every radioactive isotope has its own half-life, and there is an equation that you will need to know that relates half-life to something called the decay constant. So the half-life, which is abbreviated capital T with a subscript 1/2, is equal to the natural log of 2 divided by lambda. Lambda in this instance is the decay constant. And just like we said that half-life is measured in units of time, lambda will be measured in units of 1/time. So if your half-life is in years, lambda will be in 1/years. If your half-life is in minutes, lambda will be in 1/minutes. To calculate the number of decays that occur in a given time interval, we have equations for this. We're going to skip ahead to the one you need to know, and it's right down here. So the one we're going to use is R equals R sub 0 e to the minus lambda t. R equals R0 e to the minus lambda t. R stands for the rate of decay. There are some people refer to this as the activity, and they'll use an A instead of an R. Some people look at the number of radioactive nuclei present and they'll have an N instead of an R. Some look at the mass that you have and you'll have an M instead of the R. But the form of the equation is the same because the number of radioactive nuclei is proportional to the mass. The activity is proportional to the number of radioactive nuclei, and the rate of decay is proportional to the mass. So they're all related, and we can take this one simple equation and customize it for our problem. So if we look down, we'll scroll down to our first example. So the first example is that we have an unknown sample with a half-life of 2.6 hours. So in our knowns, we're going to have half-life equals 2.6 hours. And the question is, how long does it take? So little t is what we're trying to solve for, to go from an activity of 250 counts per second to 100 counts per second. So the 250 counts per second will be our starting rate, R sub 0. And the 100 counts per second will be our ending rate. We only have two equations, R equals R0 e to the minus lambda t, and t sub 1/2 is equal to the natural log of 2 over lambda. And you can see in this form, I've gone ahead and told you that the natural log of 2 is the same as 0.693. So you will see that if we're trying to solve for t, we're going to need lambda. We have the half-life, but we need lambda. So that's our first step. We're going to find lambda. So the decay constant is lambda. We'll write down our equation. T sub 1/2 is 0.693 over lambda. We'll plug in the numbers. So the half-life is 2.6 hours. Rearrange, do the arithmetic, and you find that the decay constant, lambda, is equal to 0.266538 hours to the minus 1. Please try not to round off very aggressively early on. Remember, in physics, we like to save our rounding off till the last step. So to find the time, we use our second equation. So we have R equals R sub 0, e to the minus lambda t. R is the activity at the time that you're talking about, so 100 counts per second. R0 was the starting activity, 250 counts per second. And then it's e raised to the minus lambda, we just found lambda, times little t. So we can't do anything inside the E until we get rid of this 250 and move it to the other side. So 100 divided by 250 gives us 0.4. So 0.4 is equal to E to the minus, and here's our lambda times T. Now, we still can't do anything inside the E. We need to get rid of the E. And the way to do that is to take the natural log of both sides. So if you take the natural log of 0.4 and the natural log of E to the minus, here's our lambda and T. On the left side, the natural log of 0.4 becomes negative 0.91629. And on the right side, when you take the natural log of E raised to a power, the E disappears and the power comes down. So on the right side, we have negative 0.266538 at 1 over hours, or hours to the minus 1, you can write it either way, times T. And now we can isolate the T. Divide both sides by this value. We have that T, I'm going to scroll down. T will be negative 0.91629 divided by negative 0.266538 hours to the minus 1. Remember that hours to the minus 1 is the same as 1 over hours. When you do the arithmetic, the minus signs cancel, and we end up with 3.437749, and the units will be hours. Time is in hours. The decay constant is in 1 over time, but time will be, in this case, hours. Okay, moving right along. We have some radioactive decays are not a one-step process. Some of them, you have your unstable nucleus, and maybe it gives off an alpha particle and forms the daughter. So maybe we have uranium-238 and it gives off an alpha and it forms thorium-234, but thorium-234 is also radioactive. It is unstable. So maybe it gives off a beta minus particle and the daughter is Pa-234. But Pa-234 is also unstable. Maybe it gives off another beta minus and turns into uranium-234. But uranium-234 is unstable and it gives off something else. And the pattern continues until we finally end up with lead-206. So we started out with uranium-238 and ended up with lead-206. That is a big change in mass. The atomic mass went from 238 to 206. And a fairly large change in atomic numbers, so in the numbers of protons trapped in the nucleus. This is a decay series. It starts out with a radioactive parent and ends up with a stable daughter at the very end. And you'll notice I haven't given you all the steps. This little dot, dot, dot tells you things are missing since we went from 234 to 206. So this is a decay series. We have 3 naturally occurring decay series and 1 artificially produced one. So if you start out with uranium-238, eventually you're going to end up with lead-206. If you start out with uranium-235, eventually you'll end up with lead-207. If you start out with thorium-232, eventually you'll end up with lead-208. If you start out with neptunium-237, eventually you'll end up with bismuth-209. This last one has to be artificially produced. Neptunium is a transuranian element. It doesn't occur naturally anymore, but these three are naturally occurring. And you'll notice that they're given names. The first one is a uranium series. The second is actinium, not because it begins with actinium, but because we already used uranium, and actinium is the second isotope created in the list. It's the first daughter. All right, let's talk a little bit about radioactive dating. How do you know how old something is using radioactive dating? Well, there are a variety of techniques, but the one people know the most about or hear the most about on the news is carbon-14 dating. The ratio of carbon-14 to carbon-12 in the Earth's atmosphere is roughly constant for quite a long time. Now, there are spikes in it. It does change. Back in the 1950s and 60s, when we had above ground nuclear testing, this ratio changed. So there are some variations, and the more we know about atmospheric science and things of this nature, the more precise we can be. But in general, this ratio stays constant. And the reason is that the carbon-14 is produced when nitrogen-14 is bombarded with cosmic rays. Well, cosmic rays are radiation from deep space. They enter the Earth through the polar regions where there's a magnetic window, an opening, and they come in and bombard the upper atmosphere. And so this nitrogen-14 turns into radioactive carbon-14. And since we assume that the rate of cosmic rays entering the atmosphere is relatively constant and that that's the primary path for the nitrogen-14 to change, then we assume this ratio is relatively constant. So as long as a plant or an animal is alive, when its radioactive carbon-14 decays, it will be replaced by new carbon-14 from the atmosphere in the form of CO2. So it'll lose it and gain it at roughly the same rate. If the organism doesn't get carbon from the atmosphere, then this technique is not as effective. You have to know a lot about its source of carbon in order to use it on something that doesn't gain carbon from the atmosphere. So when the plant or animal dies, it stops adding new carbon-14. And that's like turning on a nuclear clock. It's like you begin your countdown. You say, okay, I'm dead. No more new carbon-14. Tick, tick, tick. The amount of carbon-14 is going to get less and less and less and less over time. So we can use it as a way to figure out the age of the material. More precisely, it tells us how long the item has been dead, how long it has no longer replaced its carbon-14. What do we need to know to do this? Well, we need to know the original carbon-14 to carbon-12 ratio. We need to know the current ratio and the half-life of carbon-14, which is approximately 5,730 years. Some books round it off a little differently. This will be the number we will use if we have to calculate. Once you know these things, you can calculate the approximate age of your item. Carbon-14 dating is limited to organic materials that are 60,000 years of age or younger. If you get older than that, there's so little carbon-14 left in your sample that it's really hard to measure. And so we tend not to use it for really old things. And again, it's for organic materials. Other isotopes can be used for radioactive dating: rubidium-87, uranium-235, and uranium-238. thorium-232, and potassium-40 are all used frequently for radioactive dating. So let's look at our little example. We have a living piece of wood and we know it has an activity of 15 decays per second per gram. We've got a wooden artifact made out of the same kind of wood with an activity of 2 decays per second per gram. And the question is, how old is this bowl? So what do we know? We know that R0 was 15 decays per second per gram. We know that R is 2 decays per second per gram. And we know the half-life of carbon-14 is 5,730 years. We are trying to find the time, and we've got our same two formulas. R equals R0 e to the minus lambda t, and lambda equals the natural log of 2 divided by the half-life. So obviously, if we have the half-life, we have to find the decay constant. So that will be our first step. Find the decay constant. So lambda is equal to the natural log of 2 over the half-life. It'll equal 0.693 over 5,730 years, which is the same as 1.21 times 10 to the minus fourth, 1 over years, or 1.21 times 10 to the minus fourth years to the minus 1. Remember that since years is in the denominator, 1 over years is the same as years raised to the minus 1 power. And now we can find the time. We use our formula, R equals R0 e to the minus lambda t. So 2 decays per second per gram. I know it's written kind of funny. I apologize for that. Is the same as 15 decays per second per gram. You could have written it just like this and been just fine, because we're going to divide. And it's equal to e to the minus, here's our lambda from up here, times t. So divide both sides by 15 and we get 0.1333. And that leaves us e to the minus lambda t on the right side, where lambda is this long little digit. And remember, to get rid of the e, we have to take the natural log of both sides. Natural log of both sides. So the natural log of 0.1333 is negative 2.0149. And the natural log of e raised to a power makes the e disappear, and the exponent just plops down. So negative 0.000121 years to the minus 1 multiplied by t. And now we can divide both sides by this little funky digit and isolate the t. Notice the minus sign goes with the number. So a minus over a minus cancels, and 2.0149 divided by 0.000121 gives us 16,652.09. And the answer is in years. Time is in years in this case. Okay, last example for radioactive decay. So we start out with 500 grams of a substance that has a half-life of 45 minutes. How much is left after 1 day? So our mass is 500 grams. We've got 1 day. Now, we know our half-life is in minutes. So what did I do? Why did I turn the 1 day into minutes? Because time and half-life have to be in the same kind of units. Just like R and R0 have to be in the same kind of units. When we work with this, lambda and t have to be in comparable units, and that means we have to have half-life in the same units as time. So 1 day is 24 hours, which would be 1,440 minutes. And our half-life is 45 minutes. So as you can imagine, the first thing we do is find the decay constant. So lambda is going to be the natural log of 2 over the half-life. So 0.693 over 45 minutes, which will give us 0.0154 minutes to the minus 1. And now we can find the mass. Remember, we said that The mass and the rate of decay are proportional. So we can take this R equal R0, e to the minus lambda t, and replace R's with M's. And you can use big M's or little m's. It does not matter. So we're looking for the ending mass. We know we started out with 500 grams. We've got e to the minus lambda t. Notice we put in the right numbers. So 500 grams, when you take E and raise it to this power, you should get 2.3393 times 10 to the minus 10. Notice the units go away. And when you multiply that by 500, you get a teeny tiny number, 0.000000117 grams, or 1.17 times 10 to the minus 7 grams. We'll stop here and we'll look at radiation detectors in the last video for this chapter. So I will stop the share and stop the recording.